Okay, so welcome back. So in this session, we have 3 talks. So first one is Ragavendra. So Ragavendra, please, he's going to talk about how the ultra slow roll inflation has some unique observational implications. Please.
Thanks. I hope I'm audible. So thanks organizers for providing me this opportunity to present my work. This is based on a recent review that I published with my collaborator, Professor Sriram Kumar, in this journal Identifier and Archive Identifier. I will be mainly focusing on the paradigm of ultra slow roll inflation and the unique observational imprints it leaves and how it can help us distinguish from other models that are considered particularly in the context of primordial black hole production and secondary gravitational waves. So this is the outline of my talk, where I will first briefly introduce what ultra slow roll inflation is, how it is defined at the background level. Then I will discuss the all promising features of primordial black holes and secondary gravitational wave production arising from the enhancement of power spectrum on small scales. Then I will focus on something unique that happens only in ultra slow roll models, which is the nulling of correlations. And I will focus more importantly about the non-trivial higher order correlations, particularly the non-gaussianities arising from the 3-point correlations in these models. Lastly, I will summarize with a brief outlook of the results. So to give a broad perspective, the ultra slow roll phase has garnered attention in the literature because of their ability to enhance power over small scales. How do they achieve that? Well, we know that each scale corresponds to different observables, particularly the early phase of inflationary evolution, which I have tried to depict in this cartoon, corresponds to large-scale observables such as CMB. The intermediate evolution corresponds to intermediate scales, and late-time evolution corresponds to small scales. So if we introduce a feature or some peculiar dynamics to occur over the late-time evolution of the inflaton field, then that will get imprinted over the corresponding scales, and it can be constrained by a variety of observables which have been discussed throughout various talks in this conference. What we introduce is the ultra slow roll phase over this late-time epoch just before the ending of inflation. And to understand what ultra slow roll is, it is nothing but a stagnation of the inflaton field close to the bottom of the potential, but not quite reaching the minimum, where the kinetic energy of the inflaton drops exponentially as presented here in terms of E-folds. This can be achieved by a variety of features introduced in the potential. The widely discussed feature, of course, is the inflection point that has been thoroughly discussed in Rajiv's talk. But apart from that, even a break in the potential or a bump or dip artificially added by hand to the potential, all of this variety of features achieves essentially the same property of slowing the field down that in turn will enhance power. Moreover, we can take a slightly phenomenological and model independent approach in reconstructing the behavior of epsilon1 in terms of the model parameters, particularly just the duration of ultra slow roll and the onset of ultra slow roll denoted as n1 and delta n1. And we can faithfully capture largely the features that we require in the behavior of epsilon1, as I have contrasted the reconstructed one against the model driven behavior of epsilon1. I will contrast both the model driven predictions and the reconstructed predictions throughout the talk. Once we have the background dynamics defined as such, we will proceed to compute the perturbations at the level of power spectrum. And what we see from a plethora of models in the literature, I have just chosen 6 exemplary models, most of them motivated by various high energy theories, supersymmetry theories, and so on. For details, please refer to the paper. But all I am trying to drive at is all of them have a generic feature of nearly scale invariant spectrum over large scales, but they have a sharp dip. I will come to this dip later. A sharp rise in the power, which will lead to collapse of primordial black holes, as Rajiv has been saying, and drive, of course, the secondary gravitational waves as well before tapering off over further small scales. This can be similarly achieved in reconstructions of epsilon1 that I just said, and it is much more neater in that if I vary the parameter of the onset of ultra slow roll, I can achieve this ultra slow roll epoch at a convenient time of my interest, and that in turn leads to enhancement at a scale of my interest, which in turn leads to black hole of my mass range of interest to be produced. I won't go into the details of the computation of black holes and gravitational waves because that has been firstly covered in various talks. Also, that is not the prime driver of this particular talk. All I would like to show is that the fraction of black holes that can constitute the dark matter in the current universe can be significantly enhanced because of the enhanced power that I achieved in the models that I showed, as well as in the reconstructions, of course, with reconstructions which much more ease of tuning. And similarly, I can enhance the gravitational waves at the second order because the the gravitational tensor, secondary tensor perturbations are sourced by the square of the scalar perturbations, and they in turn have enhanced amplitudes, as similarly was what was shown in, for instance, Rajiv's talk or in Richard's talk. But what I would like to comment at this stage is that we are already going beyond the linear perturbation theory, and we are delving into the regime of non-gaussianities. For instance, even if R is a Gaussian field, assumed to be a Gaussian field, which maybe not, is sourcing something as R square, which is patently a non-Gaussian field. So all these gravitational wave signatures are non-Gaussian inherently in their nature, which cannot be discerned readily at the level of omega GW, but if we decompose into spectra, they will have non-Gaussian signatures. That is one surefire way of distinguishing these signatures of secondary gravitational waves being detected in these observatories, in contrast to other scenarios such as phase transition or stochastic mergers of black holes and so on. Then I will focus specifically on the unique signature that gets produced only in ultra-slow roll models, which is this dip before the enhancement. This enhancement, as has been discussed, can be arrived at during other phases of inflation or other models of inflation as well. But ultra-slow roll alone predicts this dip in the power spectrum before enhancing this rise. We showed in a recent work that this dip is actually a nulling of correlations, as in the scalar mode function vanishes at a specific scale. And we illustrate that using two specific models and show that the dip can be achieved at around 7.6 megaparsecond versus an intermediate scale. But to capture this dip, our previous two observables may not be of help because those are integrated effects of power spectra. We need some linear probe which is directly proportional to the power spectrum. For that, we choose the 21 centimeter spectrum emitted by H1 gas, which is just linearly connected during the dark ages of the universe to the primordial spectrum. So if we have a dip in the primordial power spectrum, the 21 centimeter spectrum within the dark ages of redshift, let's say 50, also will contain the dip in contrast to the standard nearly scale invariant spectrum, which are the dashed lines in both these models. So this is a unique smoking gun signature of ultra-slow roll models that if you detect a dip in 21 centimeter, we can start scanning the subsequent frequencies for enhanced amplitudes of gravitational waves, and we can start saying that this is arising from the same mechanism of primordial physics. This is still at the level of power spectrum, but we already ventured much into the non-Gaussian regime when we discuss the secondary gravitational waves, right? But all our statistics still somehow rely on the Gaussian statistics that we have adopted for the scalar perturbations. For that, we have to justify that the power spectrum that we compute has not been affected by the higher order correlations, or in some sense, the bispectrum and the trispectrum are not significant enough compared to the power spectrum that I compute in our ultra-slow models. For that, we can explicitly compute the bispectrum, which is defined as the 3-point function in Fourier space. And if I plot that, I see the bispectrum in equilateral limit because I have to project it in the 3-point function in some space in some limit to plot it in a 2D plot. I see that the bispectrum in all these limits, such as equilateral and squeezed limit, faithfully mimic the shape of the power spectrum and hence get enhanced similar to the power spectrum. So it may not be readily obvious that these are negligible. To make sure that these are indeed negligible in the computation of observables, we have to quantify the non-Gaussianities arising from these bispectra in the models of ultra-slow roll. So the typical way to quantify the non-Gaussianities in any given scenario is the parameter called non-Gaussianity parameter FNL. This FNL is just a suitable dimensionless ratio of bispectrum to the products of power spectrum. And once again, if I compute this parameter for the two specific models of interest, I will just focus on those two. I see that the two models left and right, they still give somewhat order 10 power minus 1 or 10 power minus 2 throughout the range of wave numbers. I will just take a moment to say what I have plotted here. The non-Gaussianity parameter has been plotted with different combinations of K1, K2, K3, such that in the regime that is plotted, each point corresponds to a specific triangular configuration in the wave number. So I am in principle scanning all possible triangular configurations in wave number and seeing if FNL, how large that FNL amplitude is in the models of ultra-slow roll. And I see that this, of course, is plotted in linear scale compared to my previous plots of log scale. So it depends on the choice of K3, which sits in the denominator of these ratios. So if I choose K3 to be the peak amplitude of the power spectrum, the wave number at which the peak occurs, the FNL has this shape of highly local shape, completely constant almost, and of order 10 power minus 1 or 10 power minus 2. But if I change the K3 to pivot scale of CMB, let's say, in the same models that produce enhancement, I still get order 10 power minus 2 as the amplitude, but the shape gets different. It becomes an equilateral shape compared to a nearly constant shape. You may still say that non-Gaussianity can be negligible. It is just a change in shape that I am seeing, which I can safely ignore because the amplitude is anyways less than 1, but not so fast. If we scan the complete range of wave numbers in various limits of the bispectrum that I just showed, squeezed limit, equilateral limit, and flattened limit for the same parameter FNL, obviously the non-trivial features that I was seeing in bispectrum and power spectrum get imprinted in this FNL, and they give rise to large amplitudes throughout the range of wave numbers, which may not be readily obvious if we see just the density plots. So there has to be a comprehensive and consistent way to account for these non-Gaussianities in our computation of all possible observables, let's say primordial black holes or secondary gravitational waves or any 21 centimeter power spectrum. And this is indeed a happening phenomenon in the literature, that people are trying to fold in this non-Gaussianity parameter in the estimates of all the observables that we compute. I will just close with one possible way to account for non-Gaussianities in the estimation of omega GW particularly. This is a work that I did to fold in the scalar non-Gaussianities. Sure. Scalar non-Gaussianities in the computation of omega GW, for which I will adopt the method of using Feynman diagrams. This is a semi-classical treatment, but I am just borrowing the same structure that we adopt in QFT to construct the Feynman diagrams. After all, they are the same order by order or moment by moment expansion. I see that if I construct a primary gravitational wave as a 2-point vertex, then secondary gravitational waves can be a one-loop correction. And I introduce the FNL, which is a 3-point vertex, which can be seen here inside this one loop to compute the FNL contributions to the omega GW, which I denote as omega GW superscript 2. So if I compute all these, this is a 3-dimensional integral. These are 6-dimensional integrals, as we all already know. I will just show the results for the two models of interest, just the two ultra-slow roll models I'm taking. The Gaussian contributions, which are shown in solid lines, are actually comparable to the FNL-driven contributions to omega GW, which are presented in the dashed lines. The 3 dashed lines are namely the 3 different diagrams that I'm showing here. Of course, this is just one set of diagrams. There may be other correlations arising due to cross correlations, and those are to be explored separately. All I'm trying to drive at is non-Gaussian contributions are indeed significant in the computation of ultra-slow roll models, and one has to consistently take into account in the computation of observables, with which I will conclude my talk, summarizing the salient features that ultra-slow roll models are promising candidate. They produce significant amount of primordial black holes, secondary gravitational waves. We already know that, but they also predict a unique feature of nulling of primordial correlations, which can be gleaned only in linear probes such as 21 centimeter from dark ages. Importantly, IISER models are highly non-Gaussian in the generation of their fluctuations, and they have to be accounted for in the computation of observables. And there is a significant effort in the contemporary literature where they treat these loop corrections as loop corrections to the Gaussian estimate arising from higher order correlations. So with that, I thank you for your attention, and I can take questions.
So I didn't quite understand why you insist on this linear power spectrum. In principle, it should also, that feature should also be there in the nonlinear power spectrum, but it might just be slightly smeared out.
You are saying which particular feature?
You said you can only see it in the 21 centimeter dark.
No, what I meant is, firstly, the density fluctuations in the dark ages are fairly linear with respect to the primordials.
Yes.
And hence we can easily see a one-to-one correspondence of the features.
Right.
But if we, let's say, take this omega GW curve, I'm computing these curves also from the same D spectra, but I don't see these sharp nulls in the spectrum of omega GW, right?
Sure.
Because they are, in some sense, for instance, I have to convolve the two mode functions to arrive at the source.
Why? Do you think that the feature vanishes at lower redshifts?
No, that is a different effect. Of course, this feature may vanish if I compute the 21 centimeter, because as the density fluctuations grow non-linearly and so on. I'm not talking about that. Even for fairly straightforward computation like secondary gravitational waves, the way in which the scalar perturbations go into the calculation is in some sense a convolution. It's R square. So in Fourier space, I have to convolve. So that may lead to filling up of that null in omega GW. So I may not see a omega GW nulling there. So that is why I said a similar spectrum like this can be produced by other models as well. Hence, they become degenerate. To distinguish is what I was driving this point towards.
Yeah, I have a question that why you see the deep in 21 centimeter is because of the overdensity, and that's why you need less photon. Physically, can you tell?
Physically, okay.
Yeah.
This is actually not related to the 21 centimeter delta TB, the global temperature itself. It is just that the density fluctuations themselves.
What I am asking.
Yes.
Dark matter.
Yes, density fluctuations themselves are suppressed at a particular scale. And H1 being a faithful tracer just traces out that particular distribution, and we are just gleaning that pattern here.
Because I'm saying if you get a suppression in density,
yes,
generally you get an enhancement in 21 centimeter brightness power. That's what
Yes, that is a separate the global. No, that plot I have not included here, but I understand that that is not what I'm presenting.
Any more comments, questions? Okay. Thanks, Raghavendra. Thank you very much. So please.